can everybody hear us now?
Yeah.
Okay, cool. So I'm realizing you didn't hear any of my introduction that I just did, but this is Jordan Armstrong. He's presenting his master's thesis defense for a degree in industrial and systems engineering. And Jordan decided it'd be best to hold questions until the end, or if you want to put them in the chat along the way.
Yeah.
All right, Jordan, go ahead.
Awesome. So start from the top again. Thank you, Quantile, for being here, and thank you everybody for attending online. I had the unique opportunity to work on a joint master's project here, where the thesis itself is in industrial engineering. So it's solving this whole class of problems. The proposing the decomposition approach to parametric non-convex regression was a joint project over at nuclear engineering. We're going to walk you guys through this method being applied to a nuclear resonance analysis problem. So in short, the entire project is curve fitting. Given a plot that looks like this, we just want to find the best curve to go through that data. And we'll get more formal with this and more into what we're doing, but this will be a picture. We'll go back to again and again to better understand the process and understand what we've done in this project. So first, we'll go through a little bit of the optimization background. We're not just curve fitting, but we're curve fitting with a non-convex function. Non-convex optimization is a hard problem to do. The picture you see on the left here is an example of a non-convex function. Why is it so hard to optimize a non-convex function? You're trying to find the global minimum, the lowest total value in that entire function. As you can see, in a non-convex function like this, there are multiple different local minima. Depending on where you initialize, is which of these local solutions you get. It can be very hard to then compare and know, is my local solution truly the global solution? Additionally, in these non-convex problems, you get areas of very high curvature or areas of a lot of flatness, but they can be hard, especially for iterative methods, such as gradient descent or Newton's method, able to handle those high curvatures or regions of flatness. So what are a couple of methods that are used for non-convex problems? The first method, well, let's make it convex. One of the ways to make it convex is called convex relaxations. So you're trying to determine these different lines to then make a convex envelope around your non-convex problem. By making all these lines, now you have a convex function that approximates your non-convex function. We can perform optimization on a convex relaxation and get an approximate solution to our non-convex problem. However, there are a few problems with methods like this. One is that finding all these approximations in these envelopes is a very computationally expensive problem. And in doing that, sometimes it's still an intractable problem that you can actually get a convex relaxation. Additionally, just because you get a solution to the convex problem does not mean that is a good solution to the non-convex problem, whether that be in the amount of time that it takes to solve that convex problem or how close that non-convex solution is to that convex solution. So another method of solving non-convex problems is just transforming the optimization space. An example of this is given a linear fractional program, which is this formulation you see here, which in this formulation is a non-convex problem. However, one of the ways we can solve this problem is using this transformation you see right here. So we take that non-convex problem you saw on the last slide, use this transformation, and now you can see we have the summation over two variables. It's now a linear program. Linear programs are very easy and very fast to solve. However, as you can tell, for solving this problem, we had to come up with this very unique transformation. So using this method is very highly problem dependent. There's a lot of work that has to go into figuring out what the best transformation is. These transformations cannot be used again and again for different types of problems. But we're also not just doing non-convex optimization. We're also trying to find that global solution. And finding the global solution is also hard. So what are a couple methods for finding our global solution? The first is cutting plane methods. So this shaded region you see here in C is the feasible region where solutions can live. And these first solid lines you see here are our constraints. So our constraints from our feasible region and the different algorithms and methods are trying to find the best solution that's within our feasible region. So what cutting plane methods do is they try to reduce that search space. Because again, the big difference between a global optimization and local optimization is comparing across that entire space. So if we can constrict ourselves to a lot smaller of a space, that problem becomes easier to solve. So we're looking to find these different cuts that then reduce that feasible region. However, it's a very computationally expensive task and a very challenging task to find these optimal cuts for your problem. And then a second method, which is a more common method, and a method that Baron, our algorithm, actually uses, is branch and bound. So the common example is looking at discrete problems. One way to solve a discrete problem is just look at every possible combination of solutions, take the best solution, and now you're done. However, running through every single combination would take a very long time if it can even be solved. So branch and bound attempts to be smart and saying, let's take our original problem, branch on one of our variables to get two subproblems, and the solutions of those subproblems give us an approximation for that original problem. And hopefully by doing this branching and solving these easier approximation problems, we can prune out an entire side of our tree and now not have to look at any of these possible combinations that exist over here. The branch and bound is just trying to take that whole enumeration of our problem, do that smartly, and now have to look at a small subset of those problems. So we see some methods for solving non-convex problems and solving these global problems. And that's what we're trying to do in our curve fitting here. We're trying to curve fit with a non-convex function and arrive at that global solution. Just using those methods that we've gone over already, trying to solve our nuclear resonance problem is still intractable, which means we can run those methods for as long as we want, and we're still not going to reach a solution. That's where our new method comes in, of how we're going to solve these problems. But first, why do you even care about this nuclear problem? So ultimate goal of this project is to create this automated reproducible tool for nuclear data analysis. So these pictures you've been seeing are these experimental data sets of a cross-section. What a cross-section is that probability of a nuclear reaction taking place. So given this probability curve, you can see we have these big spikes in these probabilities. Those big spikes or bumps in the probabilities are our resonances, and our cross-section can be parameterized via those resonances. So given this experimental data, we're going to be able to tell first how many of these bumps are there, how many jumps in the probability exist, because that number is not known, and then be able to determine what the proper parameters are to fit those resonances and provide an uncertainty on the values as well. How's this done currently? Currently, there's no automated process for doing this. This process is having to be done by hand by nuclear data evaluators, and is a very laborious, time-consuming process. So they're having to go through this cross-section data and measure out the resonances, and it takes a lot of expert evaluation to be able to do this by hand. And one of the key things in doing this by hand is that if one evaluator evaluates that data, the next evaluator, there's very little reproducibility between those two evaluators looking at that data set. It's also been demonstrated that the uncertainty that you get from these evaluators doing by hand is consistently underestimating the uncertainty that is being evaluated in the cross-section data. Underestimating that uncertainty then has complications down the nuclear data pipeline, such as in reactors where these cross-section values have to be used. So this hand-done process by the evaluators is slow and not reproducible. So how is our approach different from what's being done now? Well, it's automated. Instead of trying to have these people do it by hand, let's give them a tool where they can get that initial starting point. We can formulate this optimization problem, get a solution, and now this gives those evaluators that initial starting point to then refine that model moving forward, instead of them having to start that process by hand. By giving them an initial starting point, our method is fast and it can be reliable and reproducible from evaluator to evaluator. These evaluators are getting the same starting point in those initial solutions. Additionally, we'll be able to demonstrate that our uncertainty size is appropriate given that experimental data, as our uncertainty is coming directly from the experimental data and not having to be done by the evaluators to try to fit that data from what they think is the best fit. So how are we actually doing this? This is our next picture, kind of overviewing the entire model. We'll step through each of these pieces and demonstrate how our method works. But first, what is this parameterization that we're using to fit the cross-section? As I said before, the cross-section can be parameterized by these resonances, by these spikes you see in the data. This parameterization is a single level Brett-Wigner, which is an approximation to the full formalism. We have to use this approximation because the full formalism has complex variables, and most optimization tools do not like having complex variables. So you can see this is a highly nonlinear, non-convex function with a lot of variables floating around. So let's step through these. You can see here in the blue, these blue variables are all from our experiment or different nuclear parameters, nuclear background information that we will know. We have k sub alpha, which is our wave number, the penetrability shows up, our spin stat factor, and then this value R is the number of resonances that are present. Again, this number is not actually known, so we'll have to provide an upper bound on this value, and then allow our model to decide how many of those resonances it want to end up fitting with. So each of these resonances that you see, as we can see, this is an energy dependent function as well. So for each of those energy values that we're looking at in that window, our function has to be evaluated at each of those energy points in that window. This increases the time it takes to solve this problem and makes it very cumbersome to be able to solve. Now we see each of these resonances have 3 parameters that you use to generate this resonance. The first is the resonance energy, which physically represents the middle of that resonance, and it shows up down here in the denominator in the squared term. Then we have 2 more parameters of our 2 partial widths. We have the capture width, you see here in green, and the reduced neutron amplitude in yellow, which show up as its product in the numerator and the sum in the denominator. This term that you see, that's the sum down in the denominator, physically represents that width of that resonance at half max. And then just as a note, we are looking at the capture cross-section, and we'll be dropping this capture subscript as we move forward. This is going to be our predicted cross-section. So then how are we actually proposing to solve this problem? Well, first we need to take in that nuclear background taken in our experimental conditions and considerations. So the first were experimental functions. You saw this case of alpha and this penetrability number in that parameterization that we are fitting. All these functions are a function of our different experimental parameters. This A is the atomic weight, which for copper is approximately 63. Then we have our scattering radius, which is a known value. This constant term is this mass of a neutron, or Planck's constant. And then this L is the spin group that we're looking at. This L represents the spin, and right now we're just looking at spin equals 0. But you'll see that L doesn't show up in these equations. What L actually dictates is the form of this penetrability factor. So as you change your value of L, the functional form of penetrability will change. Additionally, for each of those parameters that we saw, for the resonance energy, for our partial widths, they follow very well-known distributions. That level spacing, that distance in between resonances, follows the Wigner distribution, and our 2 partial widths follow the Porter-Thomas distribution, which for a given experiment, we know the average values for these. What these average values do is it allows us to generate a very large training set. Why is this important to generate a large training set? Because in practice, these real experimental data sets that we're looking at, you may have 3 to 10 real experimental data sets. That's not enough to fully understand our model and how our model is fitting. So by using these distributions, we can generate a whole bunch of synthetic experimental data sets. And that way we're able to then characterize the fit of our model and any biases that our model has before it sees this much smaller test set. You'll notice that our average reduced neutron amplitude has much more figs on it. That's because this is a derived quantity with strength function and then actually explicitly given. The other thing that we need to consider is how much noise is present in our experimental data. Again, we're trying to train upon synthetic data that looks like our experimental data. So one of the key things is getting the noise in our synthetic data to match the noise in the real experiment. So you can see we have a 5 resonance example here, 1, 2, 3, 4, and 5. The only difference between that red curve and that blue curve is the noise model that we're using is a normal noise, which simulates the Poisson noise that's actually present in the experiment, and normal will approximate that Poisson very well at high count values. So cool, we're able to generate a very big training set. How are we actually then training our model and fitting these different windows? So like I said in the beginning, if we try to solve for all hundreds or thousands of resonances at once, that problem's intractable. Our algorithms will just keep running and not actually reach a solution. What we're proposing is we're going to decompose this problem into small overlapping windows that are now going to be solvable. So we're going to first assume that these windows can be solved independently. Note that these windows are going to be overlapping with each other. So this overlap then allows us to account for local interactions. Because as we'll see later, a lot of resonances like to cluster up. So by doing this overlap, we can account for those local considerations on either side of that resonance. In this initial solve, we're going to ignore any global interactions. But as we enforce our Cardinality Agreement and Parametric Agreement later on, we'll be able to use this information from our first solve to help account for the global interaction terms going on. So the key thing in our window decomposition is you have two hyperparameters you can choose from. And one is the window size, and the next is the window overlap. So the key thing here is how do you choose your window size? Because as you increase your window size, now your problem is much more representative of the global problem, but that problem is going to be much more complex and take a lot longer to solve if that bigger window is even solvable. However, by having bigger windows, we'll need less stitching routines on the back end. So you want to find that proper balance between how quick you can solve a small window versus how representative your big window is. This is a nice visual to show you what that actually looks like. So you have the left window is here in red, and the purple dashed window is here on the right. So you can see this resonance that's right here in the middle, this overlapping region, is getting seen by both windows, and any interactions to the right are captured by the purple window, and any interactions to the left are captured by that red window. So the red window and the purple window would be solved independently, and then in the next step, we're going to force those solutions to agree in that overlapping region. So now that we've broken the problem up into these small windows that are now can actually be solved, how are we proposing to solve them? There's going to be two steps here. The first will be our squared error regression to get the mean value for the resonance parameters, as well as how many resonances are present. And then we'll perform quantile regression to get the uncertainties on those parameters. So this is a single window optimization formulation. There's a lot going on here. But what you'll notice is this big old term right here is just our predicted cross-section that you guys saw earlier. Predicted cross-section you guys saw earlier. We're just trying to minimize that squared error between our experimental cross-section and our predicted cross-section across the entire window. For allowing this model, we found for the experiment that we're looking at, allowing the window to fit up to 5 resonances is ideal, and then the model can then zero out resonances if it doesn't need 5 to fit that window. The semi-continuous constraints you see here in yellow is how the model is able to zero out those resonances. These N's that you see here and the M's are the minimums and the maximums that are allowed from the distributions. So from the partial widths, we can use the Porter Thomas distribution to get the minimum and maximum physical values that those parameters can take. So we allow our model to fit these widths if they fall within those physical values. And then the semi-continuous part is also then allowing them to be 0. And then for the windows, we're just allowing the energies to be between the mins and maxes of those windows. And then there's also an energy ordering constraint. All this is doing is saying that when you get a solution for the window, your resonances have to be in the order in which they physically occur. All this is doing is stopping the model from getting stuck with multiple solutions where you have the same set of resonances with the same objective value, but you're just having resonances that are flopped with each other. So by having them be in order of how they physically occur, you stop this issue of having multiple solutions with the same objective value. What does this actually look like? Again, we're just minimizing that squared error between our experimental cross-section and our predicted cross-section. This is showing what this looks like for the one resonance case. You can see for this one resonance, we're getting a very good estimate of this resonance. In the red, this is the true cross-section value. So we don't actually know what that true cross-section is. And the whole goal of this project is to take the experimental cross-section, fit that as well as we can to get the good fit on the underlying true cross-section. So we're able to see that the true cross-section fits with a squared error of approximately 0.36. But from our fit from the squared error in black, we're actually fitting that experimental data a little bit better than the true cross-section fits. And we can see that we don't actually, in practice, know that true cross-section value, but in our training we do. That's one of the key things about the training side is that we can actually compare how well we're fitting that true cross-section since we're the ones generating that true cross-section, and see that we're getting a pretty good fit between our predicted and true cross-section values. So now we're able to get those mean values for each of those parameters, but how are we providing an uncertainty as well on those parameter values? This is where the quantile regression takes place. So now instead of doing that squared error fit, now we're just doing this, what's called the median absolute deviation. So now we have the linear term of the difference between our experimental and predicted cross-sections instead of it being squared, but we're putting it through what's called the check function. Check function, all of it's doing is trying to balance how many times is that cross-section value being over-predicted versus how many times is that cross-section value being under-predicted. How we control this tau value represents how many of those points are going to be over-predicted versus under-predicted, and thus our tau values represent our different quantiles. So by getting those different quantiles, we can get our standard deviations, which can give us our variance, which then gives us this uncertainty envelope for our parameters, which can be propagated to the cross-section space to give us our uncertainty on that cross-section. Again, what does this actually look like? So you can see here in the different colors, the different values of tau. You don't need to actually make them out here on the graph. All that's important is as we increase tau, we're increasing how often that cross-section is being over-predicted. So this blue curve here is our lowest tau value, because we're under-predicting the most. And this gray tau value is our biggest tau value, because we're over-predicting the most. One of the key things to know about doing this quantile regression is a sanity check is to see this tau value of a half closely represents a solution to our squared error problem. And our squared error should be lowest at that tau of a half, which it is. And then our squared error is non-decreasing as you step away from a half in either direction. So now for each of those windows, we can get the number of resonances that are present, an average value for each of the Rich-Moore parameters, an uncertainty on those Rich-Moore parameters, but we're left with all these windows. So how do we then get all these windows stitched back together to get them to agree to our global solution? I want to do this in two parts. The first part is getting them to the windows to agree on how many resonances are present in that overlapping region. So this is our Cardinality Agreement piece. So in our problem, the Rich-Moore parameters are physically representing how many resonances are present. So if two windows are looking at the same overlap, they should agree on physically how many resonances are in the overlap. This also helps with control for overfitting, because if one window wants to fit to noise, the other window has to agree to fit to that noise, or that ends up getting zeroed out. So how do we actually end up doing this? We can see we're going to keep our same squared error term that you guys had seen before in the objective, but now we're going to penalize that squared error by the disagreements in the number of resonances that are present. So this alpha value is our penalty that we're able to choose the value for. And then this z is our binary variable that represents how many resonances are present. So this blue term is simply just saying how many resonances does the left window see in the overlap. The red term is saying how many resonances does the right window see in the overlap. We're trying to minimize that difference. For our problem, it is better to overpredict the number of resonances than it is to underpredict. Because again, we're proposing a tool for nuclear data evaluators to use. So it's easier for them to go through and say, hey, this is an extra resonance than it is for them to say, hey, we're missing resonances, where are they? Which is why we're choosing the max function. But again, our method is problem agnostic, but for other problems that may be the min function. So we're penalizing based on how many resonances each of the windows say are in the overlap versus the maximum from those two. So if the left had 2 and the right had 3, this max is going to be 3, forcing them to try to fit that left window with 3 resonances instead of the 2 that are previously found. This is an iterative process where on each iteration where they're still disagreeing, this alpha value is going to continue to grow. Initially, that alpha value is small to try to let the windows agree by themselves, and slowly keep doubling that alpha value until we get a convergence where this term is 0 for both of our windows. So now that the windows have agreed on how many resonances are in those overlaps, we need the windows to agree on the values for those resonances as well. And this is now our parameter value agreement. So again, same squared error term you guys have seen, but now we're going to penalize based on the disagreement in the values for the parameters for the resonance. So what the vector representing inside the norm here is just the difference in our values that from the left window and the right window compared to their average value. This green term is just the average of the parameters for the 2 windows. And then we're going to take the squared of the L2 norm. So it's just looking at the relative error, the relative difference between the left and the right versus that average. And by doing this, we want to do this relative error because we have parameter values that vary in magnitude greatly from one another. Some of our capture widths are on the order of milli-electron volts, and some of our resonance energies can be up to mega-electron volts. So by introducing this relative term, now they're going to be all in terms of the relative error. That allows us to have one beta value for this entire norm instead of having to try to find different betas for each of the disagreements to account for that difference in magnitude. Again, we're going to start with a small beta value. This is an iterative process. We're going to keep increasing beta until we can get the maximum element of this difference to be within 1%. So we're able to then get, for each of our overlaps, they agree on the number of resonances and the values of those resonances. But again, this parameterization is just representing the cross-section space. And we ultimately care about the error in the cross-section space. The error in the parameter space is not as important. So what does this actually look like? In the beginning of this presentation, I told you guys one of the big cool things about this project is that we're able to generate as much training data as we want. And this is the benefit of being able to generate these large training sets compared to the small test sets that we have. Is that we can now quantify how well our model does on the synthetic data that very closely mimics that real data. The three key things in this error quantification is that we can see that our errors are normal in each of our three parameters. We're also able to account for the biases that occur in that fit. So we can see across thousands of runs that our capture width is consistently being underestimated. So now when we go to fit that test set that only has this 3 to 10 experimental data sets in it, we can account for that bias going forward, where we wouldn't be able to do that if we didn't have this large training set to train upon. Additionally, we're able to demonstrate our error band size. You can see this is an example from the one resonance space you guys saw earlier. These yellow dots are mean predicted value. The blues are predicted plus or minus 1 standard deviation. You can see that the red curve, representing the true cross-section, fits very nicely within that error band. And it's just one example of us having a proper error band size where we don't want it to be any smaller, or else we wouldn't capture it on the side here, or any bigger and we'd lose it on the other side. So cool, you saw one resonance, you saw one window. What does this look like across a whole bunch of resonances? So the example you'll see that we're about to step through is looking at a 100 resonance ladder. So we have 100 resonances that we're trying to fit. So it gets broken down into approximately 100 windows that we're solving across. What we're going to see is that our solution starts pretty well and slowly gets worse as we start adding in more windows and more resonances. So again, for each window, we're allowing it to fit up to 5 resonances per window, and our window size is twice the average level spacing. So on average, we should have 2 resonances per window. So for this first picture you're seeing here, this is the first 3.5 windows. So we can see after we go through 3.5 windows, we have 5 resonances that we have fit, and we're still seeing that our predicted squared error is slightly smaller than the true squared error, as we're trying to fit that experimental data for the experimental data is generated from that true cross section. So this is our goal, we should see that. And we can see the 3.5 windows and 5 resonances, that L1 norm between the true cross section and our predicted is very small. This is a good fit for our first 3.5 window problem. But we're not solving for 5 resonances in this problem, we're solving for 100. What happens as we look at more and more windows? Now we're at 17 of our windows. You can see now our L1 norm is about 20%, and we no longer have a predicted squared error that is slightly less than our true squared error. However, you can see that we're still doing a good job of fitting each of these resonances that are coming through. We're going to keep stepping through our approximately 100 windows. So you can see this L1 norm is slightly increased, and again, the predicted squared error is slightly more. But now this difference between these is staying constant as we're increasing to more windows here. And you can see the difference in the pink and red here, at least from the zoomed out perspective, we're still doing a decent job of getting those resonances. And now looking at 50 windows, again, our L1 norm actually went down from the 17 windows just slightly. And again, this difference between our true and our predicted is staying approximately the same. But why is this happening? Why are we able to do really well in the first few windows, do not so well in the middle, and then just steady off as we keep going? And there are a few reasons for this, or key takeaways here. One is the window size. So in that window size selection of choosing 5 resonances to fit in a window for twice the level spacing, those experiments were done on the front half of that data set you guys just saw. One of the issues with doing it on the front half that you guys just saw are these resonance clusters. As you can see visually, as we move to higher energies, that distance between resonances gets smaller and smaller and smaller. This first resonance was in a window all by itself. And then these further resonances, you're getting 2, 3, 4 resonances that are clustered together. So instead of having the optimal window size be chosen for these first few resonances, that optimal window size needs to be started from the higher energy resonances. It needs to be much smaller than that 5 that we were choosing to start with. Or future works can also look at having a dynamic window range and allowing the model to decide, hey, I'm going to start with a big window here, and then as I increase the higher energies, I'm going to decrease that window size because I need it, because now we're getting these clusters of resonances that I'm having a hard time fitting. The other key takeaway why this is happening is the optimal error function. So as I kept highlighting to you guys, we're doing a squared error. Squared error is very good at penalizing outliers due to that squared term. So our predicted cross-section and that experimental cross-section, we're not going to allow there to be any very big deviations in those. But what squared error is bad for is when you get small errors. Because those small errors, those small deviations, since you're squaring it, become even smaller. So squared error is very good at getting your solutions to be close, but not very good at moving those close solutions to be even closer to one another, which is what's happening in this as well. Because interestingly enough, this fit on this very big resonance in the start, for that window had approximately the same squared error as fitting 3 or 4 resonances in the cluster down here. It's just fitting those 3 or 4 down here. There's a lot more going on in that window, so a same magnitude fit is not giving you as good a solution. So as we increase in higher energies down here to dealing with these clusters, we need to have an error function that pushes those small errors even smaller, which squared error is not doing. And the last key takeaway from this is our models resolve resonance region. Go back to this picture again. This issue where resonances bleeding into each other, that's a physical thing that happens. If we kept going on in energies, this bleeding into each other is going to keep happening more and more, and ultimately going to arrive at that unresolved resonance region. And that region is a problem that the human evaluators have as well. So it's one of those things where eventually either we're going to run into this problem. We're about 2/3 of the way there on this problem to what physically the unresolved region is. Or that can be one of the key documentations of this method is saying, hey, this method works for the first 2/3 of the resolved resonance region, gives the nuclear data evaluator a starting guess for that first 2/3, and now the nuclear data evaluator has to just do that last third by hand. So again, it's still decreasing that workload for them and making their work easier. And showing you an example of what this actually looks like, this is a smaller example of one of the windows from the very end of that cluster. This is the experimental data you see. You don't see the error bars on it. This is just the mean values from the experiment. Looking at this, how many resonances do you think are present in this data? This is what the model is dealing with at the end. There are 2 resonances that are present. If you're looking at the true cross-section, the true cross-section has 2 resonances that are present. Our model is able to find both of those resonances still in data that looks like this. So even though those numbers don't look as good in the fit, you're able to still detect the resonances that are going on in these regions, just not to the same preciseness that you're able to get in those earlier regions. For that 100 resonance example, we're still able to find 95 of the 100 resonances. So that's the last piece that the nuclear data evaluators can do, is saying, hey, this model is able to find those. Now let me go in and just refine those values to get that last piece, make that fit just a little bit better. Again, this is the results from our quantile regression. So we're able to do a good job of saying, all right, we know how many resonances there are. We're able to get the parameter values for them, but what about our uncertainty? You don't need to be able to make out this picture either. It's just demonstrating that as we have our varying tau values, you have this envelope that's forming. This uncertainty envelope forms on the wings here and also up at the peak. And as you can see, again, stepping through our tau values, we're able to get that minimum value of our tau of 1/2. But now this is able to give that data evaluator, what size envelope do I want to have on my cross section? Because again, we ultimately don't care about the parameter fit, because there are multiple different parameterizations. There's constant work going on in the data field of, hey, what parameterization do I want to best fit the data? What ultimately matters is how well can we fit that cross section. So we can see that we're able to get very nice envelopes on our cross section, that true cross section, and then fit in our envelope as it should. What does as it should mean? Taking the same one resonance example you see here for the quantile regression, this is what that over prediction looks like that I was talking about before. So again, that tau value controls how much a cross section is being over predicted versus under predicted. These red dots, which the model does not see in its fit, represent the over prediction of the true cross section. So by fitting the experimental data, our model is able to characterize a curve, that adjusted R square of 0.999, of how much the true cross section is being over predicted. This blue curve is representing how much the experimental cross section is being over predicted. So even though we're fitting to the experimental data, we can get a very nice functional form on the uncertainty on the true cross section. So what are the key limitations and risks with doing this project? Because we're able to see a lot of good results. With any method, there are always issues or things to work on. So the first major risk is that, cool, you're doing all this training on the synthetic data. What are the synthetic data? Actually has a bunch of errors in it. It doesn't look like that real data at all. So the fellow students working on this project, Colton, actually demonstrates that you cannot tell the difference between those two data sets. Additionally, now we'll have this with any automated process you're looking at, there's always that cost of runtimes. However, running that 100 resonance example for you guys, so on the order of a few hours, we're doing these projects from nuclear evaluation from start to finish can take up to the order of a few years. Also, as we saw, we were able to only find 95 of those 100 resonances. How do you know if you missed one, or how do you know if one of those ones you found is an extra resonance? That would either have to be done by the evaluator going in and manually checking each of those, or the work by Cole, another student in our group, is this direct implementation of the Wigner importance commons distribution, which is another tool that the nuclear data evaluator can use, because Cole will be able to provide a probability for you for, hey, you found this resonance, how likely is it that that resonance is an extra resonance? Or Cole can also give you, hey, here's the probability that in this energy range, I think you missed a resonance, go check here. So Cole's able to help those evaluators by saying, these are the resonances that you should check because they're the most likely to be an extra, or these are the regions you need to go look for a missing one because they're the most likely to contain a missing resonance. And what does the timeline for this project look like as a whole? Right now, we're able to demonstrate on the order of 50 to 100 resonances, how well we can fit them with the uncertainty quantification, and do that for a single spin group. Within the next year, we want to move this project from being the 50 to 100 resonances for a single spin group into doing multiple spin groups with the spin group assignment. Should we go back to those experimental functions you guys saw in the beginning, it just changes the shape and the size of that function that we're fitting with. But the one key thing with doing multiple spin groups is now those resonances from different spin groups all fall on top of each other. There are going to be more and more of these clusters of resonances happening as we deal with more spin groups. And then within 1 to 2 years, we want to demonstrate that, cool, we can do all this training on synthetic data, but how does it actually perform on that real experimental data? So again, this whole project is not about solving the nuclear data problem, it's about proposing this method. This non-convex problem that we started with, we're just trying to fit this curve. But doing this problem as a whole, trying to fit all hundreds or thousands of these resonances at once, is intractable. It cannot be done by current methods. But that's the key takeaway from this, is that we can apply this method to any non-convex function that we're trying to do this parameterized curve fitting for. And the key things in this problem is that there are a high number of function evaluations, because that function has to be evaluated at every single energy point across that window. we have this large unknown number of parameters, where not only are we trying to get a global solution to a non-convex problem, but also let our model decide how many parameters does it want to fit with. So again, that method is not just a nuclear data problem, but any class of these problems as a whole. So with that, are there any questions?
All right, thank you, Jordan. So I think what we'll do first is invite anyone from the audience to ask any questions. And then after that, then the committee can ask questions.
Andrew, go ahead.
Hey, Jordan, very nice talk. Just had a few questions for you. You mentioned problems with having small errors squared and the minimization causing problems. Can you elaborate a little bit more on that?
Yeah, let me go grab this whiteboard that's conveniently located over here. Oh no. Oh, I guess I can just talk it through.
You can move the
Yeah.
camera if you want.
So dealing with the squared error, that shift in making the error term smaller and bigger happens when your error is on the order of 1. Because say the error is 2, you have a difference of 2 in your predicted cross section and the experimental cross section. So that difference of 2 gets squared to 4. Okay, that's why we don't want outliers. So you have an error of, say, a half between your predicted and the experimental. When you square a half, now you get an error of 0.25. When you're dealing with those errors of less than 1, when you square them, you're actually making that value smaller. So that's why squared error is really good at getting those values below 1 and getting to that small error, but then making that error smaller once it gets under 1 is hard. Do that squaring, making numbers less than 1 even smaller. Does that make sense?
Yeah, so I guess the question here is, when you're looking at this error, I mean, one way to combat that is looking at, say, a relative error or normalizing it against your uncertainty in the data, right? So for example, if you have a very small quantity or a very large quantity, sort of if you think of this in like the general linearized least squares approach or Bayesian approach, you may be able to eat it in these sort of higher uncertainty metrics. So it's I was just curious how you arrived at that conclusion.
Yeah.
Okay, and I have a few more questions if you don't mind.
Yeah.
So you also mentioned looking at this because this is training data that you sort of have the real solution to compare against, and that occasionally you have missing or extra resonances. And my question is, does it matter?
In short, no. But it's one of those things where how important is an extra or missed resonance also is dependent upon the size of that resonance. And so it's one of those things where we're going to be able to characterize the sizes of resonances that we are missing or that are extra. It's one of the things where we found 95 of the 100, 3 of those 5 that we missed had a total width of less than half an EV. So missing a resonance that has a width of less than half an EV does not contribute to that cross-section data at all. Most likely a human evaluator would miss that. So in those cases, that missing resonance.
That's exactly my point, is that, you know, when you're comparing this to say, you know, first of all, you don't know the real solution in a real world problem, right? So when you're comparing your method to say the human method, that's, I think, the metric you want to look at there is, instead of looking necessarily at how close did we get to the real solution, it's would this have mattered as compared to the real evaluation anyway, right? Because you're absolutely right. You're always going to have these sort of small resonances that, you know, when you take into account the experimental effects, they just don't matter, right?
Right. Which that's one of the reasons why in the result metrics that you see, and even in the optimization formulations, there's no penalty or there's no results that are just showing that number. Because the important part is not getting the number right, it's getting that fit to be right. But the important part in that classification of the number is, can we quantify the types of resonances that we're missing, the types of resonances that are extra, So that way the evaluator would know that information, if that makes sense.
Yep, great answer. And then just sort of the last thing, and this is more of a for my own curiosity. So I know you're using training data for this. Did you look at anything besides copper? I know Vlad has quite the interest in copper, but did you look at anything else?
I have not, no. All of my work has been dealing with copper.
Yeah, and I'm just asking because, you know, as you mentioned, with, you know, you increase the energy, the resonances start to cluster closer together. This is also a thing that happens with the mass as well. So if you decrease the mass, the resonances move higher in energy and are more spread out. And if you increase the mass, they move lower in energy and get clustered together even sooner.
Right.
So I was curious if, you know, if, for example, you train on copper, could you fit uranium? Could you fit iron? What class of isotopes could you fit given the training set? So, and anyway, very nice work, and thank you for your presentation.
Right, thank you. And the note that I'd make on fitting the different isotopes, at least in using the SLBW equations, the only place you see that difference for it being copper is in that wave number of penetrability. So looking at different isotopes, you would just change that functional form you're looking at. And so Baron, which is the algorithm that we're using, would just have a slightly different shape that's trying to fit with. So while we haven't looked at other isotopes, I would speculate that we'd still be able to get similar results to those fits.
Yeah, Vlad was also kind. I think he gave you resonances that might be approximated by that formalism anyway. So, and again, nice work. Thank you.
Thank you.
Any other questions for Jordan?
Were there any in the chat there?
No, so we haven't had any. We haven't had any in the chat.
Nobody else. Any questions from the committee?
Let's see, I don't have any questions.
Okay, yeah, I'll ask a couple.
Let's see, maybe come over here, because, or do you have a microphone there?
I can.
Okay.
Okay. So overall, very nice presentation, great work. And I'll ask a couple of questions. One is, you chose to double the alpha parameter and then the beta parameter until convergence. Is that a very standard thing? And do you think that choice of doubling versus some other asymptotic or some other increase of the alpha or beta parameters would make any difference? Is that something that needs to be studied, or it just works, doubling is fine enough?
Right. It's one of those things where
Unmute yourself, I guess. You can answer this.
it's one of those things where doubling it is kind of the simplistic way of doing it. I have seen that done in other literature, and it was one of those things where it's kind of going back to the whole, why did we just choose a squared error vector function? Because it's simple and it worked.
Mm-hmm.
And so I think moving to a more complex alpha updating scheme would benefit the process, because it's, each time we're having to increase alpha, say we can take one or two of those iterations out, we're having to do that switching routine every like 10 windows or so. So for the 100 window problem, you're taking it out one every 10, so it's like 20 less optimization problems you're having to solve. So even if you just get that slight increase or slight decrease, the number of times you're having to resolve with the new alpha, it's going to drastically speed up this entire process. So while the simple thing of doubling it works, I still think it's worthwhile later down the road to have a more clever scheme of updating that alpha parameter.
Okay, next question. For me, it's the first time I saw those intro slides, and I think this, the project overall, to me, demonstrates a nice collaboration between departments, between the applications and nuclear and the industrial engineering department for the solving methods. You showed a very general overview of optimization methods. Can you now go back and connect that to what out of that intro are we using in this problem?
Yeah.
Or how is what we're using in this problem, how does that fit into the context of that introduction?
Yeah, so unmute. I think I'm staying unmuted. I'm just the volume mic here. So the key thing in that was to demonstrate the necessity for having a new method. So the two categories that you saw for both the non-convex and for the global optimization problems like the standard practice for both of those types of problems. So it was saying that even here's what's being done, here's the common practice for solving these problems, just using those methods in itself doesn't work. That if we just stick to what we have, this problem cannot be solved. As we saw, if you give Baron the 100 resonance problem as a whole, it can't solve that. And Baron is running at least 3, if not all 4 of those methods in the background. Like we're still using those, but our method is now taking this really big problem that those methods can't solve, bringing it down into these smaller problems that now those methods can solve. So that's what our method is necessitating, is that bridge and making methods that didn't work before now work on this whole class of problems.
Okay, yeah, that's,
But in terms of the individual window optimization problem, that is using methods that you talked about into your introduction, right?
Right.
Okay.
And at least 3 of those 4 are being used by Baron.
Okay.
So,
Okay.
and especially on the whole branch and bound, because that's what Baron is named after, is being a branch and reduce, which is what the BAR is in Baron. Like those methods are still being run behind the scenes. Just in a much more complex form than what I showed you guys.
awesome. Yes, that actually answers my last question. The last question that I had is, to me, the contribution of this master's work is clear on the nuclear engineering side, right? I think that's clearly demonstrated that, especially on the uncertainty quantification and just the automation, that is the new contribution that does not exist currently. And I think you just answered the question of what is the contribution to the industrial engineering side of this thesis, is you are contributing this this window stitching method, a method to solve a larger problem that does not currently exist with the current tools. Okay. So very nice.
Like the key thing being is the 4 methods you saw in the beginning is how you actually solve like the formulations that I was showing you. So we're not proposing a new actual like solving technique. We're just proposing a new way to formulate the problems for them to be solvable. All of our work is on the formulation side of the problem, not in actual like mechanics of solving optimization formulation, which is what those 4 methods in the beginning are actually like the mechanics piece of it.
Yeah, I mean, ultimately, right, from the IE side of it, you're breaking up a already intractable problem.
You just don't have, nobody has sound.
Okay, Jordan, you want to turn it?
Yes.
So can you hear me? Okay, so I mean, from the IE side, the optimization side, you're taking an intractable problem and you're breaking it down into subcomponents using traditional, out of the box software to solve those components. And then the novelty from the IE side is how you stitch them together, right? To then get these results. So I guess the question that I would like to know, like, you're taking a big problem and breaking it down into small chunks. Like, what's the trade-off in time, right? I mean, the size of the small chunks you break it down into is something that's controllable. How you decide, as far as the time it takes Baron. Well, first of all, why Baron? But then how do you decide the right chunks to break it down into, like based on like solving times?
Right. And so, okay.
No.
So there's an echo.
Hughes sound is on. I think.
Technology is great.
Your speakers?
There's no echo now.
Yeah.
So why Baron? That was kind of just what was proposed by the group to use as the solver, and Baron's kind of one of the, if not the, like state-of-the-art solver for global optimization problems. And how we're determining the trade-off between time and solving the problems is that goes back to the whole window size, and that is it better to have a window, have 100 windows with 5 resonances, or have like 200 windows with 2 resonances. And that just comes into those numerical experiments of choosing the optimal window size. And that for our problem, we chose to have the window sizes be on the order of 5 resonances, because that was about the maximum window size we can have to have those problems still be tractable. Where if we move to having 6, especially if we move to 7 resonances, now those windows are not solvable again. So for us, at least, it was better to have a more representative window with a bigger window size and have those windows take a little bit longer to run, because even if you break it down into the smaller windows, you're still getting the same solution in terms of the numerics of it, but the answer of how the time changes, I don't have a direct answer for how the time changes with the window size.
Yeah, it may be interesting just just to have a graph on window size versus time to completion. And I mean, presumably, right, the smaller the windows, the worse the results are going to be, right?
Right.
So have maybe some chart that says, window size, time to solution, and then also window size error, just to kind of, there's some sweet spot in the middle, right? Of what's practical and what's good. So that may be interesting to look at. So I guess like the Y barren, like what the problem is a nonlinear problem, nonlinear objective. I'm trying to go back. Nonlinear objective function with then you have the discrete constraint or the semi-continuous variable constraints, right?
Sorry, say that again.
I mean, the problem itself that you're giving to Barron, is it? I still in the Y Barron, like, is the problem very nonlinear? Is that like why? I guess why would? Do you have a better reason the Barron other than that's what you're told to do?
And so I'm partially confused on the question, but
Well, he's asking, yeah, why use Barron?
compared to just like another solver.
Well, you could talk about what would you have used if you didn't use Barron?
Right. And so I'll answer this in two parts. One is that the big part of the problem came from the nonlinear part and the non-convex part of that SLBW formalism, where that parameterization of fitting the resonances was very nonlinear. And so that's the difficult part of that problem to solve, and why we moved to using a commercial solver like Barron. Now, there's also a trade-off in using Barron, and that in some of the branching strategies that it used, because that's a big part of solving these problems is the branching bound, and that we had noticed in digging into the mechanics that it wasn't always branching as well as someone who has domain knowledge would. So that was the next aspect of this project, was to move from using a commercial solver, because we initially used a commercial solver like Barron to focus on the formulation piece of it. And the next step would be moving to actually coding up our own solver, where we can do a smarter version of branching bound that then takes into account like the probability distributions of those widths, where we can branch on the capture width and use that distribution, say, hey, these values are more likely or less likely, then hopefully have better branching techniques moving forward. So the next step in the project would be coding up our own, but using a commercial solver like Barron was to make the mechanics piece of it easy, so we could focus on the formulation piece of it at this stage in the project.
Yeah, I don't know how much you've looked into actually what Barron is doing under the hood, but and I don't know is an appropriate response, but do you know, like, so Barron is using branch and bound, but is it also using like the convex relaxations at each subproblem? Is it doing like the spatial branch and bound is like a combination of the convex relaxations and branch and bound? Is that how it's solving these problems?
Yeah.
Okay. And also, so are there tolerances on how you solve Barron that are there optimality, feasibility gaps that could potentially, like, you're not necessarily solving the problem to exact optimality, right? Because there's the tolerances come into play. Could that have a ripple effect in some of your results? If you don't get the exact optimal, you're, a little infeasible.
Yes, and that was, I think part of that too goes back to the whole squared error thing, where a earlier experiment that I was able to demonstrate was in most of these windows, just using Barron's pre-processing tools, which I don't know the exact specifics of the pre-processing tools, but just in the pre-processing gave you the same solution as doing pre-processing and doing branch and reduce for multiple hours. Where doing that branch and reduce wasn't getting you any better of a solution. So I think part of that has to do with the squared error objective function, and part of that has to do with those gaps and tolerances that you're talking about as well, where again, we're able to get that good solution, but not make that good solution a great solution.
Okay, cool.
Okay, any other questions?
I don't see any chat.
Okay, well, let's go ahead and thank Jordan. Well, that ends Jordan's thesis presentation. So thank you all for coming. And committee can just stick around a little bit and talk with Jordan and then and so.